street. The same old thing we did last week. Not a thing to do but talk to you. Oh, yeah. Hello, Wisconsin!
I just got a new laptop, but I'm not sure if I should get a warranty or not. I'm not sure when it'll fail.
Bro, how would we figure out when it fails though?
Bro, maybe we should break it even more. How about we use the Weibull distribution?
Weibull.
Weibull. Weibull.
Can I have some of the popcorn, bro?
Oh yeah.
What are we talking about?
Weibull distribution from Stats 550.
Weibull.
Bro, isn't Weibull distribution used for life expectancy of products so consumers are bound to buy an extended warranty?
Talking about conspiracies, man?
Bro, we come up with the best ideas here. We should probably make a PowerPoint.
Weibull.
For this video, we are talking about the Weibull distribution, which is a continuous probability distribution, which is commonly used for modeling a product's failure rate distribution over time. It can also be used for assessing product reliability and to analyze life data or survivability. So we're going to go over three distributions where there's a 3-parameter, 2-parameter, and a 1-parameter. So first one we're going over is the 3-parameter Weibull distribution. The 3-parameter Weibull PDF, which is f of t equals beta over eta multiplied by t minus gamma over eta to the power of beta minus 1 multiplied by e to the negative t minus gamma over eta to the beta power. And yeah, so that's where f of t is greater than or equal to 0 and t is greater than or equal to gamma. Beta is greater than 0 and eta is greater than 0. Gamma is between negative infinity and infinity. And yeah, that should be used for sample sizes of data sets that are greater than or equal to 20. And this tells us the failure-free period between time 0 and the time of the first failure. Gives us a greater insight into our data. And the 2-parameter Weibull PDF is given by the setting gamma equals 0, which is f of t equals beta over eta times t over eta to the power of beta minus 1 multiplied by e to the negative t over eta to the power of beta. This is used for modeling life data, predicting operational life of products or systems, warranty predictions when making reliability predictions. So for the 1-parameter Weibull PDF, it is like the second parameter, the 2-parameter one. Gamma is set to 0 as well. And for this one, we want to have a better understanding of the product or the subject itself, meaning that here it says b equals c, or a constant. So f of t equals the constant divided by eta multiplied by t over eta to the power of c minus 1 multiplied by e to the negative t over eta to the power of constant. The only known parameter in this one is eta, which is the scale parameter, and this is used for very small sample sizes. Like I said, the estimate of beta, which is the shape parameter, must be already known in order to use this distribution. One advantage of using this is that the data sets with few or no known failures can be analyzed. And the PDF of the Weibull distribution is f of t equals 1 minus e to the negative t to the gamma power, where t is greater than or equal to 0 and gamma is greater than 0.
The mean, or in the case of the Weibull distribution, mean time to failure of the probability distribution function is provided by the variable of t bar T-bar can be determined for the 3-parameter Weibull PDF or the 2-parameter Weibull PDF. The mean of the 3-parameter Weibull PDF is given by T-bar equal to lowercase gamma plus eta times the gamma function evaluated at 1 over beta plus 1. The mean of the 2-parameter Weibull PDF is very similar to the 3-parameter, where T-bar equals eta times the gamma function evaluated at 1 over beta plus 1. The only difference is that you do not need to add the parameter of lowercase gamma. The uppercase gamma function of both the 3-parameter and the 2-parameter means can be defined by the integral with bounds of 0 to infinity of e to the power of negative x times x to the power of n minus 1 dx. Sometimes eta can be mistakenly equal to the mean time to failure T-bar. However, this is only true for the case of beta equal to 1 when dealing with 2 parameters. Now on to variance and standard deviation. The variance of the Weibull function is represented by sigma. Sigma equals eta squared times the gamma function of 1 plus 2 over b minus the gamma function squared of 1 plus 1 over b. The standard deviation is normally the square root of the variance. Given the Weibull characteristics, the standard deviation is represented by sigma t. Sigma t equals eta times the square root of the lambda function at 2 over b plus 1 minus the lambda function evaluated at 1 over b plus 1 squared.
Alright, so now we're going to go over the moment generating function, and this is basically the function of our logarithm, which will give us the moments of our Weibull distribution. Our first moment obviously is going to be the expected value, the second moment is going to be our variance, third the skewness, and fourth kurtosis. And basically to find out, we're going to evaluate the mean at e to the t log x, and that's going to be equal to our scale parameter to the power of t multiplied by the gamma function of t over beta, which is our shape parameter, plus 1. So basically, to find our moment, if we were evaluating our first moment, it'd be t as equal to 1. We would put in our specified shape and scale parameter that we wanted to use. Each moment, it'll get you the function that we need to evaluate.
So kurtosis is a measure of whether the data are heavy-tailed or light-tailed relative to a normal distribution. So for the Weibull distribution, the formula for kurtosis is eta to the power of 4 multiplied by gamma evaluated by 1 plus 4 over beta minus 4 multiplied by gamma 1 multiplied by standard distribution to the power of 3 multiplied by the mean minus 6 times the mean squared times the standard distribution squared minus the mean to the power of 4 all over the standard distribution to the power of 4, and all of that minus 3. For data sets with high kurtosis, they tend to have heavy tails, which are outliers, and then on the other hand, data sets with low kurtosis tend to have light tails or a lack of outliers. There are two main ways to find the estimates of the parameters of a Weibull distribution. The first way is graphically, by drawing it out onto a probability plotting paper, and the second way is analytically, by using least squares / rank regression equations, or by using maximum likelihood estimation. So for this next example, I will show you how to find the estimates of the parameters using the first method, by graphing it onto probability plotting paper. I will walk you through all the steps you need to find the shape, scale, and location parameters. So for this example, there are 6 products tested, and the time until failure is given below. Those times are 93, 34, 16, 120, 53, and 75 hours. So the first thing you need to do is to rank the time to failure in ascending order. After that, use the equation that the red arrow is pointing at to determine the median rank of each product, where the I is the failure order number and the N is the sample size. Next, plot the times and their corresponding ranks onto a piece of probability plotting paper. After that, draw the best possible straight line through all of these points. Then calculate the slope of the line by looking at the values on the top of the paper. The slope of the line is actually the estimate of the shape parameter, which ends up being 1.4. So after calculating the shape parameter, draw a straight horizontal line at the ordinate point until it intersects the fitted straight line. I put a red arrow showing the point where it intersects. When you're done with that, draw a vertical line until it crosses the abscissa. I put a blue arrow pointing out the vertical line. The value at the intersection of the abscissa is the estimate of the scale parameter, which ends up being 76. So the third parameter, which is the location parameter, is utilized when the data doesn't fall on a straight line. In this case, if the curve for MR versus T of J is concave down, and the curve for MR versus T of J minus T of 1 is concave up, then there exists a positive gamma. And then if the curve for MR versus T of J and MR versus T of J minus T of 1 is concave up, then there exists a negative gamma.
All right, so we're going to use the PDF, and we're going to basically try to calculate our PDF using the Weibull function. So basically, we're going to open up RStudio. We're going to open up our PDF.R, and we're basically using two libraries here. We're using the survival library and the serve_reg_sense_cov library, and that'll give us the functionality of our Weibull function. So let's say you wanted to calculate a PDF of a sample where t equals 10, and it has a shape parameter beta equals 1.5, and a scale parameter eta, which equals to 50. So basically, to get the PDF of this function, we're just going to use the dWeibull, which will get us our PDF. We're going to send in our x, which is our population size, our shape size, which is going to be beta, which is going to be 1.5, our beta, and eta, which is going to be our scale parameter. And it should come out with 0.1.01226851, which is the PDF of our function. As Angelo mentioned with the CDF, it's actually very similar to our PDF in the way that you code it, but we're just going to use a different function. So here is our PDF code, or our PDF code from last time. So basically, we're just going to do p Weibull, our same parameters, which is t, beta, and eta. And if you don't remember what those are, our t is our sample size, our beta shape parameter, and eta is our scale parameter. And basically, we just need to run this, and that will calculate the sample size. So if we run this all together, then we should get not only our PDF, but also our CDF, which is going to be 0.08555936. So you may be wondering where Brian got his graphs for his Weibull function, his estimate parameters. So basically, we're going to show you how to graph this in R using this data set. So if we go into R right now, we'll start with a brand new script. We're going to basically initialize another library, and that will give us the functionality that we need to graph this Weibull function. So we're going to be using Weibull R this time instead of survival, and this is because Weibull R has that graphing capability. And first off, we're going to basically get our failures, and this is just going to be a variable that's going to hold all of our failures that have happened with our last data set. So in our data set, we have time to failure and different hours. So we're going to basically graph that. So in our failures variable, we're going to have 16, 34, 53, 75, 93, and 120. And those are just, again, all the time to failures that we have from our problem. Next thing we're do is make a best fit line, and we're going to use the mrrw2p function. As you can see, determination of Weibull fitting parameters. So this is basically a function that allows us to graph a Weibull function with two parameters, and our two parameters are going to be our failures, which we are graphing, and then we're going to set s equal null. S is just going to stand for successive, but since we don't have any in this data set, we're just not going to graph it. We're going to show our bounds, so we're going to set bounds equal to true, and we're also going to show our graph. And basically, if you want to highlight it all to run it, it will run. If you run it, should show up this graph, which matches not only our unreliability up to 99%, but it also has our data plots with a best fit line and our two upper and lower bounds. All right, so lastly, what we're going to do is going to plot a sample of random data. We're going to basically get our sample, and we're going to use the rWeibull function, and we're going to use a sample of 100. Our scale parameter is going to be 1.5, and our eta, our scale parameter, which is going to be 5,000. 1.5 is our shape parameter. And basically, we're going to do p points, and it's going to be sort our sample, a equals 0.3, and this will basically just get a random sample of 100 data points. But because in R, we don't have any like actual Weibull function, we'll be using the negative log 1 minus p, and that will get close to possible the graph of the Weibull plot. And basically, if we run this, it will show us 100 different data sets, and as time increases, so does our failure rate. So as you can see in our item here, it's correlated through as time increases, so does our fail rate. So it's a positive correlation between those two.
Okay, so going back to the example we did in our intro, for our real data set, we're going to test whether or not it's worth it to get a 2-year warranty for a laptop. So for our real data set, we're going to use a sample size of 10 and the laptop being the model 2017 13-inch MacBook Pro. So the failure rates listed below are the amount of days until failure. And now we're going to use the Weibull distribution function in R to find out if it's worth it or not to get the 2-year warranty.
So we're going to be using, like what Brian said, our Weibull distribution in R. And basically I have our computer failures here, which are just the days where our computer has failed. And basically we're going to use this MRRW2P, which is a 2-parameter Weibull function, basically graph and see if it's worth it to run. So we're going to run this distribution, and it's going to come up with our scale parameter as 763, which is going to be basically our average. That is going to be above our 2-year warranty of 730 days. So it would not be worth it to buy the warranty because it's greater than the days that are covered by the warranty. But also, this probably isn't a very good computer if it doesn't last for 2 years, so I would not suggest buying it in the first place.